Hello, I'm Sarjanak from Google Cloud AI. Today I'll present you our work, TabNet, Interpretable Tabular Data Learning. Tabular data is the most common data type of the addressable AI market. We observe more tabular data problems than image, video, text, or audio data problems. On the other hand, canonical neural network architectures for tabular data have been underexplored, and still, most of the applications are being dominated by variants of ensemble decision trees or other methods. In this work, we propose a novel, high-performance, interpretable deep tabular data learning network, which we name as TabNet. If we look at decision tree-like mapping, what we observe is that with appropriate design, such functionality can be also implemented with canonical neural network blocks. Here we have a simple example where we have two features, and on the left we have this architecture which is composed of multiplicative masking, linear mapping with fully connected layers, then ReLU, then linear aggregation, and then softmax. And we show that by appropriate selection of the model weights, this decision tree-like mapping can be obtained, and we can get these sharp transitions. In this work, our goal is to outperform this decision tree-like mapping while getting inspired by it. So we have these four principles in our design. We use sparse instance-wise feature selection based on learning from the training dataset. We have sequential multi-step architecture where each decision step contributes to a portion of the decision. We have improved capacity with nonlinear processing, which is the power of deep neural networks, and we mimic ensembling with higher dimensions and more steps to control the capacity that I will describe in more detail. So TabNet overall utilizes a sequential attention mechanism to choose which features are selected and then processes these features towards an overall aggregation. Here, we have a simple example of adult income classification. So this tabular dataset consists of various categorical and numerical features, and the task is to predict whether the income level is above a threshold or not. And here, in this example, we see that TabNet first selects these professional occupation-related features, processes them, then transfers the information to the next decision step, which then selects the investment-related features and processes them and transfers the information to the next decision step, and so on. And at the end of each decision step, the processed information is used towards an overall aggregate information that is used for overall reasoning. So while designing the end-to-end architecture, we also have these three principles to reflect the best aspects of deep learning. So TabNet inputs raw tabular data without any feature pre-processing. And our goal is to push the performance limits while inputting the raw data and see how much the representation learning can be enabled from raw data towards very high performance. Second, TabNet employs a single architecture with gradient descent-based end-to-end learning. And this enables many other applications such as sample-efficient domain adaptation, semi-supervised learning, generative modeling, and so on. All these have been successfully demonstrated for image and text data thanks to end-to-end learning. And we show that with TabNet also, this high-performance end-to-end learning can open such horizons. And lastly, our goal is to build interpretability into deep neural network architecture design. So a lot of the ensemble decision tree variants have interpretability built in relatively simple ways. And here we consider interpretability in two kinds: local interpretability, where we get explanations for each sample separately, and global interpretability, which is about the amount of contribution of each input feature to the trained model aggregated over all the samples. Here I show the overall architecture of TabNet. So we have these two blocks, feature transformer and attentive transformer, at each decision step. So attentive transformer basically processes the representation from the preceding decision step and then outputs the multiplicative mask to be used for feature selection. then the feature transformer is applied on the selected features and returns the representation, which is then partially used for overall decision making via this linear aggregation and partially transferred to the next decision steps attentive transformer input. And here the detailed designs of feature transformer and attentive transformer are shown. I will describe these in detail next. The attentive transformer is composed of linear mapping followed by batch normalization followed by multiplication with the prior scale term, which is denoted by this P matrix here, then followed by sparse max nonlinearity. So sparse max nonlinearity is a normalized activation function which has sparsity inductive bias built in. And this prior scale term basically is the term that represents how much each feature is used thus far up until the decision step. And we obtain it by multiplying these terms, gamma minus the masks of the previous decision steps. So at a high level, if gamma is very large, then these terms will be very similar for all the features, and there won't be much of a difference coming from this multiplication with P. And if gamma is close to 1, since some of these entries will be close to 1, those entries will be very small when we subtract it, so those features will be discouraged to be used again. So in summary, by choosing an appropriate gamma, we can control how much a particular feature should be reused. And this is an important inductive bias. And especially if some of the features are redundant, typically we prefer a smaller gamma. Then we also have sparse deregularization as a form of an additive objective function. And by selecting the coefficient of this sparse deregularization term, we can also control the sparsity of feature selection. Then for feature preprocessing, we have this feature transformer architecture. So this architecture is composed of these layers, which have linear mapping followed by batch normalization followed by GLU nonlinearity. So here you see that we have some layers that are shared across decision steps and some layers that are decision step dependent. So since the inputs are shared across different decision steps, sharing also some layers allows more efficient representation learning, whereas also having some layers that are decision step dependent increases the capacity of the model. I would like to go over some of our experimental results next. So here, first, I'm showing the results on these 6 synthetic datasets. So these datasets are constructed with these following relationships, and these are very nonlinear relationships. An important property of this dataset is that the output depends on only a subset of the input features, and therefore, if the training dataset is small, the model can easily overfit to irrelevant features and can suffer from poor generalization. And here we show that this no selection rule, the standard deep neural network, would give poor performance on these datasets with small training dataset because of this overfitting to irrelevant features. And if we try to compensate it with traditional feature selection mechanisms like tree-based selection or lasso regularization and so on, the improvement we get is not very large. On the other hand, if you look at TabNet, we observe very significant improvement compared to the standard approaches. And TabNet's performance is even greater than global feature selection case here. So here global refers to the assumption that we knew which features were important by leaking that information into training to see how much the performance can be pushed. And we can see that TabNet gets very close to this benchmark and even outperforms it in some cases because of instance-wise feature selection. And next, we are demonstrating TabNet on some real-world datasets. So this one for its cover type, we show significant outperformance compared to ensemble decision tree-based approaches, and also AutoML tables, which is a commercial tabular data learning solution which searches over various machine learning models. Then we have this poker hand induction dataset. So this is interesting because here the input-output relationship is deterministic, and indeed rule-based algorithms can get perfect 100% accuracy, but conventional decision tree or standard neural network architectures like MLPs are poor at this task because the required operations like sorting and comparison are very hard to learn with these standard architectures. On the other hand, with TabNet, we show very high accuracy on this task, and this is thanks to the appropriate feature selection and using the deep nonlinear processing on the selected features which improves mimicking of these sorting and comparison type of operations. Then we have this example, Sarkos robotic arm regression problem. And again, we show significant outperformance. And here, the interesting thing is that even with a very small TabNet architecture, we can still get very decent performance compared to other complex ensembles. And on this dataset Higgs, again, we show significant outperformance. And here, the small TabNet performance is on par with state-of-the-art sparsification methods such as sparse evolutionary training. And here we don't have any specific sparsification mechanism in TabNet, but we just have judicious architecture design, which allows very compact representation learning. Then we have this Rossmann retail dataset. Again, we show outperformance, and we have some more KDD datasets. Then I would like to briefly go over some ablation studies to show the impact of different design choices. So we have a few key hyperparameters that allow us to control the capacity of the model and balance between overfitting and underfitting. So number of decision steps and number of units are some important ones. Then we have shared layers and decision step dependent layers, and it's also an effective way of increasing and decreasing the model capacity. And there's typically an optimal that combines a mixture of those. Then we show the importance of the specific form of the feature transformer block that we used. So if we replace that with very simple layers, we can still get decent performance thanks to the overall architecture design, but the performance is slightly worse. Then we show the importance of sparse feature selection, and we have the two mechanisms I described by selection of the appropriate gamma and the sparsity regularization function coefficient. And lastly, large batch sizes are typically important for tabular learning with TabNet. I would like to then go over the interpretable to results briefly. So first, I'm showing the results on this synthetic dataset, where by construction, only 4 features were the important ones that determine the output value. So for this dataset, the optimal TabNet has 4 decision steps. And we see that after training, each of these decision steps correspond to one feature. So the masks are learned so that each decision step is filtering out one feature. And if we look at the aggregate mask, we observe that model capacity is fully utilized on the relevant features and irrelevant features are filtered out. And this is even more interesting on this synthetic dataset, where we have this last feature, and based on the value of this last feature, either the first 2 features or the next 4 features are selected, and these 4 features are irrelevant. And we observe that the TabNet feature selection mechanism learns this sample-dependent feature selection very efficiently. And if we look at the aggregate mask, we have this kind of functionality where the last feature's value determines whether the first 2 features or the next 4 features are being focused on. If we look at interpretability on real-world data sets, so here we have comparisons on adult income classification, and TabNet gives consistent results with some widely used explainable to methods. And this one is showing the decision manifold of the TabNet output and the impact of the most important feature on it. And consistent with TabNet's feature importance, we observe the high dependence of the output on this important feature. Lastly, I would like to go over this new capability enabled by TabNet, self-supervised learning. So this is very important to push the performance limits, especially when we have abundant unlabeled data. If we look at the recent progress of self-supervised learning for image or text data, we observe that there are two things that enable this. So one of them is attention-based, carefully designed architecture, and this second one is appropriately chosen self-supervised learning objective function that enables very efficient representation learning. For tabular data, having these motivations in mind, we propose this self-supervised learning mechanism. So we have the TabNet encoder based on the TabNet architecture, and this is used to learn representations of the raw tabular data. Then we propose this self-supervised learning task of guessing the mask columns. And the high-level idea is that since there is some interdependence between different columns, even if we mask some of them, the model should be able to guess the mask ones accurately. And while learning this, it will enable efficient representation learning. For example, if someone has high school education, then there should be some range for capital gains. Or if someone has young age, then there should be some limits on what education level they have and things like that. And learning this representation allows the model to get an idea on the general structure of the data set. And to get the tabular outputs, we proposed a simple decoder architecture that is connected on top of the encoder architecture. And we have this unsupervised pre-training stage on the unlabeled data set. Then we take the pre-trained encoder architecture and we have supervised fine-tuning stage. And this is done on a small labeled data set. Then we obtain the overall TabNet architecture. And here the TabNet decoder architecture is shown. It is simply composed of feature transformers followed by linear aggregation. And again, this is a multi-decision step architecture similar to the motivations for the TabNet encoder. And the exact form of the self-supervised learning task is formulated here. It is defined as a regression loss function between the predicted and the ground truth column values for different samples. And masking here is done randomly at each iteration. And here are some results. Especially in the regime where we have very small labeled dataset and very large unlabeled dataset, you observe very big performance gains. And very interesting aspect is that also the convergence is very fast after having the unsupervised pre-training stage, which suggests us that the model already learns very accurate representations of the raw data. So with small number of supervised fine-tuning steps, then the model can converge to a very optimal point for end-to-end decision making. And lastly, TabNet was started as a research project for us, but then we also put effort into productionizing this on Google Cloud, and it is available there to be used conveniently on various tabular data tasks. And we already have a lot of important enterprises using TabNet on their high-value tabular data problems. So if you're also interested in that, you can check it out. We also have TabNet available on GitHub as open source code. Thank you, and I will be happy to answer questions.